Alright, so let's do some examples. So if we consider the span of 1x. So this notation this doesn't mean a vector, so maybe I should use brackets to denote a set. This is a set 1x, say x cubed. So what does this mean? Well, this is the set of all things, so this is all possible, well, let's just say it's everything that can be written some number, so say some number, I'll just say a times 1 plus b times x plus c times x squared plus d times x cubed. So it's everything that can be written in this form here. And of course this is just, something like a plus bx plus cx squared plus d, because, anything times 1 is just anything. So the span of this, the span is all cubics. You get all cubic polynomials, degree 3 polynomials, because if you consider everything that can be built out just using these 4 pieces, everything you can build out, so you can scale each individual component by any number, and so that leads you to being able to construct any degree 3 polynomial. So the span of these 4 things, which are themselves, you can think of them as functions, the span of these 4 functions that I circled in red gives you all possible cubic polynomials. So that is an example. Okay. So how do we calculate? How do we actually do calculations? So how do we determine if a vector is or isn't able to be built? So how to determine if a vector is inside some span. So that means, this is the same as saying, answering the question, so can we build some vector out of some specified vectors? That's the same thing, because if you're in the span, that means you can be built from the set of vectors. Okay, so here's an example. So let's say 9 to 7 is not in the span of, so I'll give you 2 vectors, 1, 2, minus 1, and 6, 4, 2. Okay? So, and how can we see that? Well, if it were in this span, so that means we can't actually build it. So if it were, that means that we could write, and I'm going to write things as a column, you'll see why. So I can express the vector 9 to 7. The question is, can I write it as some number, so say a times 1, 2, minus 1, plus some other number b times 6, 4, 2. Actually, maybe I'll use x's and y's instead, just to be fun. So could I, if it were in the span, that means, so is this possible? So let's just say, is this possible? So can we find, for some numbers, x and y. So the question is, can we actually build this vector here? Can we build this vector over here using these 2 specified vectors? And of course, if we could, then that means we can find these coefficients, x and y, to make it equal true. And I just want you to see that this is really just becomes a matrix equation, because we can express the right-hand side as a product of matrices. So this becomes the matrix equation. 9, 2, 7 is equal to, this is just the same as doing 1, 2, minus 1, 6, 4, 2 times the vector xy. You can just check that if you use matrix multiplication here, you can check that matrix multiplication here gives you all of that. So there's a very concise way of doing that. So in other words, asking whether or not this vector is in this span is the same as saying, can we solve this matrix equation? Okay, so in order to answer the question whether or not, so the original question is this vector 927, so can we build 927 using these two vectors? So we just rewrote that as a column, so it's the same thing, and we obtain this. This is a matrix equation. We're trying to solve for some unknown matrix. It's a 2-1 matrix, it's a column matrix, where it comes down to seeing if we can possibly find out what this 2-1 matrix is. And I'll leave it to you to see if you can try to solve this, but the answer is no, you cannot solve it. So that is how you deal with these things. Okay, so in general, I'll tell you the method. So in general, given a set of vectors, say v1 through vk, to see if some other vector, say u, is in the span, let's just go through the definition. What does that mean? Well, that means that we can write, there's some combination, some number times v1 plus some number times v2 plus some other number down to k. We should be able to write this. That's literally the definition. That means we can take a linear combination. So on the left side, we wrote down some linear combination. So this is some linear combination. And that should give us, linear combination should give us u. That's what it would mean to be in the span. And so you want to solve this equation. And so the trick here, at least if you're dealing in Rn, so the trick, if your vector spaces are just regular Rn's, is to use column vectors. So if you use column vectors, then that means that this is going to be kind of annoying because we need to specify. And so I'll use so the notation is not very good. But anyways, because it's going to be the opposite of what you think about. So let's write, for example, let's just say the vector v1. I'm going to write that as the column. I'll write it as v1, 1, v2, 1, v3, 1, down to vn1. So you write like v1 looks like that, right? v2, because v1 is a vector in Rn, so it has some coordinates, but you want to think of them as columns. So like v21 would be vector, v2 would be v21, I get confused. v1, 2, v2, 2, v3, 2, down to vn2, and basically the notation isn't that important, but you just visualize them as column vectors, and when you do that, then this equation here just simply becomes a matrix equation. It becomes the matrix, exactly what you would think. It becomes v1, 1, v2, 1, v3, 1, vn1. This represents v1. I'm just going to put that above here. And then you have v1, 2, v2, 2, v3, 2, vn2. That represents v2. And you go until you get to the last one. So that's v1n, v2n, down to oh sorry, we only have k vectors, so that would be nk. So sorry, these are only k's. All right, it's very confusing. And that gives you n1 and nk. Okay, so I'm being very schematic, and you want to solve that's equal to u1 to uk. Okay, of course, you can just check that that gives you what you want. So the point is that answering the question of whether or not you're in the span is the same as just solving a linear equation. So I'm still going to be abstract in general, but I'll illustrate this a little bit more clearly in R3, so you can see how it works in R3. So if your two vectors, so if your vector is, say, v11, v21, v31, and if your other vector is v12, v22, v32, okay, and then you want to ask, so the question is, can I build some other vector, u1, u2, u3, out of these vectors? That means I can solve this equation here. So you ask this. Again, the notation is bad. You could just use different symbols. You could, instead of using these double subscripts, you could write one vector as like x, y, z, and the other vector, like p, q, r, whatever you want. But anyways, you see that this is literally what it means. You're trying to express one vector written as a column over here as a combination of two other column vectors. But the reason it's convenient to write it like this is because then you can express this as just a single matrix equation. That matrix times this matrix equals u1, u2, u3. And so you can try to solve this equation. So, this and that will be given. You'll be given the set of vectors, and you want to. So here, these denote the set of vectors. You have these two vectors, and you're asking if I can combine these two vectors in order to get some specified third vector. So in order to do that, you have to figure out what the proper coefficients are. The coefficients here are the n's, and so your goal would be to solve this matrix equation for the red matrix.